Now let's start our journey with double complexes. A double complex in the abelian category. If you don't like abelian category, you can think of it as the category of R modules. It's a collection of objects denoted by E sub p, q, where pq are integers, and rightward morphisms and upward morphisms. There's a remark we need to make about superscripts. The first entry in the superscript will denote the column number, while the second entry in the superscript will denote the row number, as you can see from this diagram. As you can expect, these arrows, we call them d-ups and d-rights, will satisfy a couple of axioms. The composition of a d-right with a map next to it is 0. And similarly for d-ups. For convenience, we sometimes just write d-up or d-right without superscripts. So these first two axioms can be rewritten as d-right square equal to 0 or d-up square equal to 0. And furthermore, as you have expected, each square in this double complex should satisfy some commutativity condition. And here we require either each square is commutative or each square is anti-commutative. To avoid confusion, let me add that means either all the squares are commutative or all the squares are anti-commutative. We do not allow such a bizarre situation when like 30% of the squares are commutative while the 70% of the squares are anti-commutative. And there's another remark we want to make. Without loss of generality, we may assume that all the squares are anti-commutative. This is because suppose all the squares are commutative. We can transform this double complex into a double complex where all the squares are anti-commutative. So how do we achieve this? We will do this by replacing these two arrows, by replacing them with the product of some power of the -1 with this arrow itself. d-right composed with d-up equal to d-up composed with d-right. Then the second square will satisfy this equation, because this is a -1 times -1 to the pth power. And from the first one you get the sum is equal to 0. By this way, we have transformed a commutative square into an anti-commutative square. From the double complex, we can construct a corresponding single complex denoted by E dot. This E dot is defined by setting E superscript k to be the direct sum of all E sub I, k minus I. There will be an associated differential d from E sub k to E sub k plus 1. To see how this d is constructed, let's first draw a diagram. What we need to do is to construct map D from the direct sum of objects along this dotted line to the direct sum along this dotted line. So how do we do that? In the category of A modules, there's an obvious way to see what this map D is. For each element X in E sub P, Q, D of X will be defined by D right PQX plus D up PQX. In the diagram, there are maps in here, and in general, we notice that E sub K consists of the elements of the form where each X sub I, K minus I belongs to E sub I, K minus I. And furthermore, xi k minus I is 0 for all but finitely many i's. So we can extend the definition of D from each summand to all of E superscript k. And you can verify that D composed with itself is always 0. This is because D composed with itself is equal to D right plus D up square, which is further equal to D right square plus D up square plus D right, D up plus D up, D right. The first two terms are 0 because each row or column is already a complex. And the third term is 0 because of the anti-commutativity. You may wonder how to define D in the general abelian category setting. Let's restrict our discussion to first quadrant double complexes. By this we mean double complexes whose objects satisfy EPQ equal to 0 if P is a negative integer or Q is a negative integer. In this case, each E sub K is only a finite direct sum. And by the knowledge of abelian category, we know that finite direct sums always exist in abelian categories. Now to define D, we consider the following diagrams. For each PQ such that their sum is equal to K, there are two ways we can get from EPQ to E sub K plus 1, which is the direct sum of E sub I, K plus 1 minus I. There are two immediate objects, EP, Q plus 1 and EP plus 1, Q. There are four arrows connecting them. D up PQ from EPQ to EPQ plus 1 and D right PQ from EPQ to EP plus 1 Q and iota so P, Q plus 1 from EPQ plus 1 to EK plus 1 and iota P plus 1 Q from EP plus 1, Q to EK plus 1. Now let's define D. For each P and Q such that P plus Q is equal to K, we consider the following diagram, where iota P, Q plus 1 is the embedding associated to the direct sum, and so is iota p plus 1q. Now we define d sub p comma q from e p comma 2 to e sub k plus 1 by e sub p comma q equal to iota p cubes 1 composed with d up pq plus iota p plus 1q composed with d right pq. Now we look at three objects, ek plus 1, ek, and epq. What we just defined is the arrow from epq to ek plus 1, denoted by d sub p comma q. Notice that ek is actually a direct sum. This direct sum has e sub pq as a summand. So there's an embedding associated to this direct sum from epq to ek. Now we can use the universal mapping prop definition of the direct sum in abelian categories. By the universal mapping property, let's map from ek to ek plus 1, making this triangle commutes. And we denote this dotted arrow by d. This d is also unique with respect to this commutativity condition. I think I need to add a superscript to this d. So if we write this process down, we can say by the universal mapping property of direct sums, there exists a unique map d superscript k from e sub k to e sub k plus 1 such that d sub k composed with iota pq is equal to d sub pq for any pq such that p plus q is equal to k. Now we need to show dk plus 1 composed with dk is 0 for any k. For any pq with p plus q equal to k, we consider the following diagram. The map from epq to e sub k plus 1 is 0 arrow. By the universal mapping property of e sub k, which is a direct sum, there's a unique arrow from e sub k to e sub k plus 2, making this triangle commutative. Since this dotted arrow is unique, it must be 0, simply because the 0 arrow satisfies this property. Now, to show that dk plus 1 composed with dk is 0, it suffices to show, let's look at this diagram, that this diagram is commutative for each pq with p plus q equal to k. Because once this is true, d sub k plus 1 composed with d sub k will be same as the 0 arrow from e sub k to e sub k plus 2. And we are done. So now let's show d sub k plus 1 composed with d sub k composed with iota pq equals to 0 for any pq such that p plus q equal to k. If you still remember our definition in the previous page, I mean this definition, you will notice that this term is actually equal to d sub pq, and d sub pq has an explicit formula here. So d sub k plus 1 composed of d sub k composed of delta pq is actually equal to dk plus 1 composed with dpq, and which is further equal to dk plus 1 composed with the sum iota p q plus 1 composed with d up pq plus iota p plus 1 comma q composed with d right pq. And here again, we can combine dk plus 1 with iota p comma p q plus 1, as well as dk plus 1 and iota p plus 1 comma q, and we get dp q plus 1 composed with d up pq plus d p plus 1q composed with d right p comma q. Note that d sub p comma q plus 1 and d sub p plus 1 comma q have their own definitions, namely these two sums. So the previous equation is equal to the first sum composed with d up pq plus the second sum composed with d right pq. Now we can reorganize the last equation. This map cancels with this map after composition, so that this map with this map, because they are arrows in vertical complexes and horizontal complexes. So this gives us the sum of two terms in the middle. But if you look at this equation carefully, you will get iota p plus 1 q plus 1 composed with something we have already seen before. So notice that this term, this sum in the parentheses, is actually 0 because of the anti-commutativity. So the equation is just 0. And we are done. From the double complex, we can construct a corresponding single complex denoted by E dot. This E dot is defined by setting E superscript k to be the direct sum of all E sub I, k minus I. There will be an associated differential D from E sub k to E sub k plus 1. So now we have got a single complex. And this single complex is always called the total complex of the double complex. The cohomology of the total complex is sometimes called the hypercohomology of the double complex. But we will just say it is the cohomology of the double complex.